welcome to be here. So for today, we invited Mr. Brian, the founder of, Ryan, I'm sorry, the Smith, yeah. The founder of one company, and then to do the speaker for us. So today's title is the metrology in the photovoltaics. And then the talk will last 30 minutes, and then we have 10 minutes Q&A, all right? And while you enjoy the food, be quiet, and then remember sign your role for today, okay? Yes, everybody need to sign your role. So now is Dr. Senior's turn. Give us the introduction on our speaker, all right? Thank you.
Thank you, Dr. Lily. Again, would like to welcome all of you guys. It's a great pleasure to have you and to have Ryan Smith as our speaker. Just to give you a little bit of background about Ryan, Ryan is the founder of Portis, and Portis is basically a privately held company that was established in 2012. And Portis is offering hardware design and consulting services primarily to the photovoltaic portion of the renewable energy sector. So Portis enables renewable energy breakthroughs through better data. And just to give you a little bit of background on Ryan, he has a bachelor and a master degree from in material science and engineering from the University of Michigan. And he's also an American Society for Quality certified Six Sigma Black Belt, certified manager of quality and organizational excellence, and certified quality engineer. So a lot of certification and a lot of expertise when it comes to quality and engineering. So he has metrology experience in both the semiconductor and renewable energy, the ISO 17025 test laboratory program development, and he has worked for major semiconductor manufacturers and at the U.S. Department of Energy, which is the lab, the National Renewable Energy Lab. So he has quite a lot of experience when it comes to not only designing equipment using metrology equipment, and he's worked for some very important companies and laboratories as well. So today, Ryan is going to talk on the topic of electrical and optical measurements and how they play a crucial role in diagnosing performance, refining device design, and driving innovation in photovoltaics. So in this talk, he's going to explore how measurements basically drive performance improvement, and he's going to explore two emerging measurements methods that promise fresh insights into PV behavior in the field. So without further delay, Ryan, we would like to give you the floor, and we look forward to your talk, which is, the title is Metrology in Photovoltaics. So Ryan, just before you start, let me go ahead and push the record button here, and then we'll get you going. Terrific.
I won't go through this a lot, but say I've been in metrology in one form or another throughout my career. So Advanced Micro Devices and a spin-off company called Spansion here in Austin, Texas. The National Renewable Energy Lab, where I did primarily work in field reliability of PV modules, with responsibility mainly for measurement systems, data collection, analysis. And then I formed Portis, as Hubert mentioned, about 13 years ago, to focus primarily on providing measurement systems to the R&D side of the PV reliability kind of community. And my interest is in developing systems for measurements that don't exist yet. So where we're looking at either new failure modes or are interested in something that will help improve photovoltaics reliability. So in general terms, what is metrology? It is in the broadest sense, the science of measurement. Really focusing on developing, maintaining, and applying reliable measurement standards and techniques. And it's to ensure the accuracy, precision, and consistency. So you want to be able to measure something in one lab, make the same measurement in another lab, and get the same result. That is ideally what we want for this very collaborative photovoltaics industry that we're in. So what are the measurements? Well, in the most basic sense, it's things like a length, a temperature, a pressure, a weight. Well, these are very basic instruments. Some of them are shown here. They can be improved upon, and now we have bench instruments that are high precision. There's a bench DMM shown here. To what I used in some of the early area of my work in semiconductor, which was these extremely advanced measurement systems for performing measurements on nanometer size structures. And so there's been a progression and improvement in measurement systems over time. Well, when we get to photovoltaics, we don't have necessarily all of the same measurement needs as some of these other groups. But we're primarily interested in knowing at the cell level, that we've created a good product, that in the module, those products, the cells, have been put together into a form where they'll function the way that we want, and that in the field, that they are performing the way that they are expected to. Well, why are we interested in what's going on? I'll put a couple quotes here. Some of these people, you may recognize their names. One accurate measurement is worth 1,000 expert opinions. This is Admiral Hopper. If you cannot measure it, you cannot improve it. And the long version of that, if you can't measure something, you can't understand it. If you can't understand it, you can't control it. And if you can't control it, you can't improve it. These are some of the real bases of a lot of the quality systems where measurements are important. And then I particularly like this one because this is what I do. Measure what is measurable and make measurable what is not so. And that comes from Galileo. In the PV industry, it's not just the company making the cells or the modules, right? These go out into large scale utility scale systems, gigawatts of capacity, where the real goal is to generate revenue. Ultimately, there are climate initiatives and other things, but the companies that are building these want to make money. And so it's the economics that's really important. And a subset of that really is risk reduction. And so they don't want to build a plant where it is unknown the quality of those modules. It's unknown whether or not the system is going to perform the way that it should, especially over whatever length of time they've anticipated that system will behave. And so this boils down to one term, which is really common in the PV area, which is bankability. So that's the degree, in photovoltaics anyway, the degree to which a specific solar technology, so that could be like the cell technology, a component, that could be modules, inverters, what they call balance of system equipment, or a project is considered acceptable and reliable by those providing the money, the financiers and the investors. So what they're looking at is the technical track record of the companies, so proven field performance, the manufacturer reliability, they want stable product, high quality, the economics of the project, whether or not the projected revenue is really going to happen. And there's a term that is batted around a lot, which is the levelized cost of energy. And then risk mitigation. How likely is it that the companies that built these products are going to stand behind their equipment or their product? So that's warranties, and the operations and maintenance contracts kind of come from that. So a service company that provides maintenance is going to have a much better feel for how they're going to address the costs of maintaining that system if they know the reliability and the kind of track record of the equipment that's gone in there. So ultimately, all of this is to give confidence to the investors and the financiers of those projects, to then the owners of those projects, and those who are purchasing the energy that's being produced. So they want confidence that they will generate the expected energy, so that's revenue. Confidence that the system will be reliable. That comes down to cost, right? Their ability to maintain or replace failed equipment, things of that nature. Over the expected lifetime of a system. And it used to be that a system might be 10 years, 15 years. Now we're talking about systems where 30 years is a often projected lifetime of a PV system. So to get all of this confidence, one area is what is the reliability of the individual components? So consistent performance over the operational life of a component or system is the reliability definition. Well, who can help produce this confidence, this reliability data for the investors? There are R&D laboratories, manufacturers, the project developers and owners, O&M providers, and grid operators. They all want this reliability, and they're the ones who can also provide data back to the investors to show that the choices that are made are the correct ones. And so how do we get this information? Well, it comes down to measurements. So there can be electrical measurements, optical measurements, and then a whole bin of other measurements. And so that's what we're really going to kind of talk about today. So where do we perform measurements in the life cycle of a module or of a PV system? There's the R&D and manufacturing side, so measurements on raw materials, on the cells, and on the modules themselves. I didn't put it up here, but there are also measurements on the balance of system components like inverters and things of that nature to show that they're working. There's field down at the bottom, installation. So measurements can be performed right after installation to show whether there was rough handling, walking or standing. What this gentleman's doing on these modules is not best practice. During installation, sometimes tools gets dropped on the modules. Visually, they maybe look okay, but they may not perform. And so there are measurements that are performed there. Part of that comes down to handing over the project from the installation group to the operator. Field performance. This is the majority of time where the life of a module or a system will be. So the electrical performance, thermal, optical, and then meteorological measurements are as kind of a side, which is important for modeling and showing that the system is doing what it should do in the given weather conditions. And then an interesting subset of all of this is extreme weather. So we know with climate change that there are increasingly strong storms, sometimes in areas where it has not historically happened. And so that system, maybe that was installed 15 years ago, may not be built to handle some of the weather that we experience today. So it's important for us to take a look at measurements for wind, rain, hail, lightning, snow load, right? So weight on top of modules, and ice, which is important for trackers and other moving systems. This is a whole list of measurements, and I don't expect you to read through all of these, but it's just to show you that there's a lot of measurements that are out there. Many of these have very specific purposes. I'm not going to talk about all of these today, but I will leave this kind of general comment, which is the capability of the measurement system. So the uncertainty in the measurement, the stability over time, and the responsivity must meet or exceed the purpose of the measurement. So if we're interested in, say, irradiance, the measurement of light, and it takes our device a minute to settle out because it's a very slow response device, that's not very helpful for modeling like fast behavior of clouds. So we have to have the measurement meet the purpose. Increased capability generally means increased cost. So you don't want to over purchase or over design a system if it's not giving you any value. And so it's finding this balance between the right measurement with the right capability for the right cost. And it's a very dynamic environment where 1 year to the next, many of these needs change. So all of these measurements over time by all these various laboratories have led to this wonderful improvement that we've seen in the industry, which is that overall efficiencies of the cells have increased. So this plot is a very famous one from NREL, gets updated every year, where they're showing the record efficiencies for all different technologies, both historical, kind of traditional silicon, as well as emerging technologies. But what you see is we keep improving over time, and this all has to do with the ability to measure a product, improve upon it, and build the next generation. And it just is a wonderful example of the ability for us to improve upon a technology. In addition, that has also led to costs coming down. So as modules and cells become more efficient, we get better at manufacturing them, the quality goes up, and really the infrastructure around all of this fabrication improves, costs come down. And so you can see in all the different types of systems that are available, residential, commercial, utility, we've seen a decrease in cost over time. So this is dollars per watt. This is from an NREL report. The link is on this slide if anyone's interested in learning more about this. And I'll say as a side, there are links or references to a lot of these slides. So if you are interested in some of this data on any of these slides, look for those. The other thing is that as manufacturers have gotten better about thinking about their warranties and their product warranties length has increased. And I apologize, the red boxes somehow moved on me here. But from 1996 through 2022, you can see the improvement from 10-year warranty to a 25-year warranty, now to a 30-year power output warranty. These are guarantees the manufacturers are giving that these modules will produce. Generally, it's some linear degradation over time, but it'll produce for 30 years as they've stated in their documents. And so we've seen this improvement as efficiencies have gotten better and manufacturing has gotten better. And the measurements that are conducted both at the lab level and manufacturing, as well as in the field, really lead to the confidence that these manufacturers get in putting these warranties out on their product. And of course, they have a vested interest in making sure those numbers are realistic, because a plant owner can go back to a manufacturer and say, your product is degrading, it's no good, you need to replace all these modules. And so if it doesn't meet the warranty degradation rate, then they have a problem. And so it is important to them that they get this right, so that we all have confidence in the products. What I will talk about are the first three in the electrical category first. So that's AC power generation. This is by far the most common measurement in the field. Maximum power point monitoring, and then the light current IV or current voltage or IV curve. So I just took a snapshot here to kind of give you an idea of these types of measurements. So in the AC power generation, we're usually getting the data from the inverter itself. Now, the inverter is the piece of power equipment that converts the DC of the module onto the AC for the grid. And it includes generalized measurements for voltage, current, and power, but on the AC output side of the inverter. This is by far the easiest data to get. Almost all inverters offer this, and so this is kind of the de facto standard for saying, is my system producing energy and how much is it producing? Now, I will say that this data is generally not of high enough quality for it to be used for revenue. So almost all utilities and grid operators will require their own independent metering, which is generally a higher quality or higher class of metering, in order for them to pay out. And so this is a useful measurement for, am I operating as well as I was yesterday, but not used for billing purposes. Max power point monitoring can also happen at the inverter level, or it can be independent. But here we're looking at the DC side. So this is, what are the modules or strings of modules doing? And so these measurements give us a basic level, usually at the string level or the inverter level. And what we see are things like, is the DC operating point suppressed? Are strings producing as expected? And so if you look at the two plots, the one on the left and the one in the center, I want you to look on the 17th, that day, 02-17. So you see the yellow line, that is an inverter on this particular site, and it ramps up and then it goes flat. And this is because it's reached the maximum output power that this inverter is capable of, right? Well, if you look at the DC side, what happens is you see this suppression of the DC current, also in the yellow line. This is because the inverter has gone into something called clipping, where it's moved off of the peak operating point in order to keep the inverter from trying to overproduce. And so this is one of the comparisons, one of the signals that people can look at to see, well, what's going on in my system and how is it producing? So there is a correlation there between these two. The last one on the right is a very common field diagnostic. It's not usually implemented on systems, in any long-term sense, but usually this is for commissioning of a system, or you're trying to diagnose an issue. And here, this measurement looks at strings or at modules usually, where you sweep from either the short circuit to the open circuit or vice versa. And it tells you about what's going on in that string and how is it behaving at all of these different operating points. And the four graphs shown here show a shadow moving across an array. And you can see that the red, the power point or power plot, begins to get suppressed as those shadows move across. And we go from this nice, really smooth curve to this really jaggedy curve. And so these kinds of measurements can tell you things about shadowing, but it can also tell you about broken connections within modules or highly resistive components. And so IV curves are, I would argue, the most common field electrical measurement for diagnostics. The other two are primarily for long-term analysis, long-term monitoring. On the optical side, I'm going to talk about these first three, which is electroluminescence imaging, infrared thermography, and then visual inspection. Electroluminescence is, I would say now, probably the most common optical technique. And it's not purely optical. It does require electrical stimulus, but the information we get is through means of an optical device. So what happens is a current is forced through the module, and those cells luminesce in the infrared. So you can't see it visually, but you can pick it up on special cameras. And you get images like what are shown here as an example, where you can see the cracks and you can see the disconnects in the cells. So these very dark areas are where pieces of the silicon are no longer connected to the rest. And so they are, in this case, not luminescing, but in a production side, they're also not contributing. And so this can tell you things like whether a module has been mishandled, whether or not extreme weather and other events have led to cracks in the cells, And as severe cases, these types of issues can cause your whole plant to not behave as it should. It moves off of the best operating point and really suppresses the overall production in the plant. And so it is a very important diagnostic technique. It's very common in manufacturing, right? They want to show that they are putting out high quality modules without broken cells. Very common in laboratories. In the field, it can be done with handheld equipment, but now there's a whole industry that's popped up with drones where they provide a stimulus to an entire array or subarray, and they fly a drone overhead taking images in this in these wavelengths. It's often done at night, but they can build an entire array of images and really identify what's going on with good precision. One of the older techniques, but still very useful, is what's in the middle, which is infrared thermography. Often done, I guess, during the day as opposed to the EL. Here we're interested in what's getting hot. And so it's a different wavelength range. We're really looking for high resistance paths. So these are things like bad connectors that's shown in one of the images there. Failed diodes, which can lead to thermal differences, and that's shown in the bottom image. Hotspots, which are cells that are, for one reason or another, heating up during the day when energy is being produced. And these hotspots can lead to safety issues like fires. I don't have any pictures in here, but you can Google some PV fires and they're dramatic. But you can see there that there's a significant difference in temperature. I mean, these can get very hot. So this is again a good diagnostic technique. It can be done from a distance, and so people will go into the field and they can look across an array and look for hot areas within an array. I will say the key for this is that you don't get a reflection from the sun, because the sun can reflect and show as a hot area when it's not really. It's just a reflection. So IR thermography is an important technique. And then visual inspection. This is, you'd argue, well, this isn't really a measurement. Well, it can be, because here we're looking at counts. How much of the array is impacted by a particular failure type, or how prevalent is a certain amount of soiling, things of that nature. So it does fall under the measurement bin. But here it's inspections of arrays, usually ones that have been out in the field for a while, looking for things like material failures, cracks in the backsheet, which is often a polymer. More common now than it has been is glass backsheet. Damage to the glass itself. Encapsulant, which is the polymer that kind of holds all of these modules together. Encapsulant delamination or browning. This can happen due to exposure to environmental contaminants, moisture ingress, things of that nature. Delamination can happen because of like thermal cycling over time. And then identification of like natural hazards, soiling issues. So there are a couple images here of soiling that builds up around clamps. I got this picture at one site with a lizard that had built a little home inside an enclosure. Plants that grow up that cause shadows on PV systems. So some of this may not show up in the electrical or the optical measurements, but walking through a field, it can be easily identified by humans, right? We're much more capable of taking the broad look at and ingesting what those potential problems might be. So those were some general overviews of like the most common. We could get into a lot of detail on a lot of these others. We just don't have time. But I wanted to introduce you to the first of two techniques, which is more emerging. And so it is an electrical measurement. This one has been termed V10. It's one that is kind of near and dear to me. I'm looking into this technique. And it stems from this plot, which is module floppiness is increasing. So what do we mean by floppiness? PV modules have a given dimension in length and width, and then the thickness of the frame and the thickness of the glass. Over time, modules have gotten bigger. They've gotten longer, wider, and the frames have gotten thinner. Part of this is because technologies have improved. We're able to make thin glass more readily, more cost effectively. We are able to make cells thinner. And there's economics, which is most of these frames are aluminum. And they want to minimize the amount of aluminum that goes into a module. And so when we take a simple ratio of the length times the width, right? So the area of the module divided by the height times the glass thickness, we see this trend. And you can manipulate this equation, height plus thickness, whatever, but you get the same general trend, which is that modules are getting longer, wider, thinner, and so they're floppier. And so part of the motivation for this V10 measurement is to say, can we identify cracking in cells or damage to the module before it shows up in some of these other techniques? And can we do it cheap? And can we do it fast? Right? These are all the things that we want to be able to achieve in a good measurement. So this is an animated GIF. I'll just let you look at it, where module was in the lab and damage was introduced. So these are things like tools being dropped on the module, all the way through the last ones, which is where somebody walked across the module. And what you can see is the electroluminescence images on the top. This is a great visual for the benefit of that measurement technique. And then on the bottom, you have two plots. The one on the left is what's called dark IV. This is a measurement taken truly in the dark, no illumination, but you're forcing a current through the module. And then on the right, which is an illuminated IV. So you have light shining on the module, and you're measuring that IV curve. So ideally from short circuit current, which is 0 volts, all the way through the open circuit voltage, which is at 0 amps. And so what you see is a very little change in this light IV until you get to substantial amounts of damage. Well, I told you that this technique is one of the most common in the field. So if you had some small level of damage that happened either in shipping or installation, and you take a traditional light IV curve, you're not going to see that damage. And also, you're not going to necessarily see it in an electroluminescence image, especially taken from a drone in the field. The resolution is just not good enough. But what we do see in the dark IV is a substantial change. These curves are almost entirely unique from each other. And so they are measurable. So if we look at that dark IV curve and we look at the delta, the difference between the original pristine condition and the worst condition, and we can measure like, what's that gap? What's that voltage gap between all of these? We end up with a plot like this, and it peaks at about 10 milliamps. And so what this means is if we perform a measurement at 10 milliamps, we have the greatest chance of detecting a change because that's the current at which we see the broadest response. And so V10 is then defined as the voltage required to inject 10 milliamps through a module in the dark. And there's a lot more data I have in the appendix if we have time for it, but this is to show you kind of what those changes are. So in V10, we can see a 33% drop in voltage when you only see a 5% drop in the light IV. That's this bottom row. All of the cells shaded in red are within the measurement uncertainty of the equipment used for that measurement. So for light IV, generally 3% uncertainty is what is common in the literature. And for V10, it's about 1%. And so we can see that we can detect damage with certainty, which is important for confidence, well before it can be detectable with confidence in the light IV. So this is an emerging technique. It is coming up primarily through silicon, but we are applying it to thin film and other silicon architectures, newer architectures, to show that this has broad applicability. And I think the key items for this is that it's low cost, low power, fast, and it's a permanent change in the module. So it means that it's a very stable measurement. Whereas you look at things like electroluminescence or light IV, those are very labor-intensive measurements. Light IV requires a person to go and connect to each module or to each string and perform a measurement, and there's a higher uncertainty with it. Electroluminescence is, again, labor-intensive, requires somebody to hook a stimulus, so an electrical source, up to the modules in the dark, fly this drone over the array, making sure that they don't crash into things and damage, modules. And then somebody or a system has to go and analyze all of those images. And it takes a tremendous amount of power for an electroluminescence measurement. Nearly on the order of the amount of power that that array or subarray produces during the day. So it's extremely energy intensive. Whereas V10 measurement is on the orders of a few watts, so very implementable. Let's see. I'm not sure my time here, so stop me if I'm going too slow. The last one here is vibration we'll talk about. So here we're interested in what happens in areas where wind will lead to vibration damage. So here are two pictures, one of a tracker where modules have basically peeled away from the tracker due to high winds, and then a very large array where fixed tilt, but the wind just picked up and ripped these modules off of the structure. So these are very extreme examples, and obviously we can identify that there are problems here. But what happens when you have vibration that is very strong but doesn't lead to visible damage like is shown here? So this comes from a poster. You can look at the whole poster, I guess, Hubert, if it gets shared. That's being presented next week at a workshop. But here is a technique to measure the vibration in modules and on other components of a structure with very low cost. So this uses MEMS sensors. MEMS are micro electromechanical systems. It's generally a sensor on a chip, but it's got a moving part. So in this case, it has a little floating weight inside that tiny little 2.5 millimeter square device. And it's a wonderfully produced class of devices that has led to a substantial cost reduction for the measurement industry. So all of your phones, for instance, contain these types of accelerometers and other MEMS devices. And so we experience them every day. We're just not necessarily privy to them. But this uses a couple dollar accelerometer, and it's not, we don't show the data here, but a pressure transducer that allows these measurements to be performed with very low cost, so that we can learn a lot about these really dynamic environments in these very large array fields. So with this device, we measure the acceleration in 3 axes, so X, Y, and Z, and the graphic is shown here. And we take the data, analyze it. So the red section here is what was analyzed in a FFT, a fast Fourier transform of the acceleration data to find out, well, what's the frequency at which we see vibrations, and we can distill tens of thousands of these measurements, and that was what was done on these 5 sites, 2 at Dr. Hubert's site at UCF, and 3 of them at the National Renewable Energy Lab. And my colleague at NREL, Dr. Jordan, put these together. It shows like the winds and how the winds change over geographic location. So at UCF, most of the winds come out of the south, so kind of southwest through southeast. And at NREL in Colorado, the wind is almost predominantly out of the west. And so very different wind conditions. And so you could imagine that a tracker in one location is going to behave differently than a tracker in another location. And this is a lot of information to distill here, but what it shows is the frequency at which we see a lot of vibration. And so he divided this up into different wind speeds. Suffice it to say that the modules on the fixed tilt, so this is the UCF, kind of behave the same because it's on this rigid structure. Modules in Colorado on a tracker behave differently than the fixed tilt, and they also behave differently from the structure that they're attached to. So that's what's called the torque tube. And that at high wind speeds, we get very different behaviors between the torque tube and between the module. And this has a lot to do with how, or can influence how these structures are designed going forward. So we're just getting into this, but because these MEMS devices have been developed and we can now produce them in mass with relatively low cost, we can perform measurements over wide swaths of array without it becoming prohibitively expensive, which is what it has been in the past. I think this is the last slide, second to last. But what it shows you is this tracker at NREL, where it moves over the course of the day. So in the beginning of the day, it's facing east. At noon, it's flat, right, facing straight up. And in the evening, it faces west. And I wanted to just point your attention to the red and the blue circles. Both of these are the intensity at 6 hertz. So how often are we seeing 6 hertz vibration? So 6 times per second. And you can see the blue, there's a dip at noon, which means that this torque tube, the structure the modules are mounted on, really isn't vibrating at 6 hertz at all at noon. But then we see a lot of vibration at 6 hertz in the modules as they sit there and flutter. So, what we can do is begin to understand these really dynamic conditions and hopefully produce better and more reliable equipment and installations going forward. Okay, so a couple last comments. We do measure a lot as an industry, and I will say perhaps too much. There's this old adage that, it used to cost a lot to make a measurement and to retain that information. Now storage is cheap, so let's just measure everything. That sounds great, but it means that somebody has to be looking at it, or a system has to be looking at it. So I think we have to, as an industry and as people who might go into measurements, and I think you could perhaps take this to a lot of industries, is strike a balance between what is useful and what is just overwhelming. If there's too much information, sometimes it just gets set aside and nobody looks at it. Increased capability often comes with increased cost, is not always helpful. We don't need to measure to the nth degree if a simple measurement will suffice. So that additional capability, that higher quality sensor, it may just end up being a cost, but not really improve the overall benefit. Measurement quality is everything. This is the flip side, is that the measurement quality must meet the requirement or it's not useful. Well, if we need a very precise measurement, but we're measuring it with a poor quality sensor, it's not useful, right? The uncertainty could be so large that we don't have any value in that measurement. So you do have to match what you need with the capability of the equipment and make sure you're at least at that minimum. And this is, again, one that's close to me, is measure where our understanding is lacking. So I'll say if the measurement doesn't exist, imagine what it would take to make that measurement, go invent it, and then prove to the industry that that works. And that's really some of the motivation for V10 and or what's coming out of V10 and the vibration work is right now for us to prove that it works to our colleagues in the industry. I'll leave you with the last few things, that nearly every field of study can benefit from measurement. It doesn't have to be a technical field, but measurements exist even in very disparate fields, right? You've got archaeology and economics and very technical engineering. Measurements can be helpful everywhere, especially if it allows you to improve what you're doing. And the last quote is a famous one from W. Edwards Deming. He's one of the founders of quality movement, which I think it kind of sums up a lot, which is in God we trust, all others bring data. So I think that's it. Thank you.
Thank you, Ryan.
Thank you very much. So we have any questions? Don't leave yet. We have a lot of the summer program opportunities will be introduced, okay? Yes. So any questions? Dr. Rinsford have a question.
How often do you take these measurements of these systems?
How often
how
do we take
often
measurements?
Required, yes.
So I would say for the most common measurements, which are the AC measurements and DC measurements, I'd argue that most are taking it at 1 minute. 1 minute sample. There are some sites that do 15-second data, and then they post-process it into 1 minute. So, 1 minute seems to be pretty good. It used to be 10 years ago, 15 years ago, 15-minute data was enough. But with the ability for us to do more meteorological modeling and investors wanting a higher fidelity, most sites have gone down to 1 minute. I don't currently see a lot of benefit going faster than that, but there could be a use case. For things like the vibration studies and others where we are interested in these high frequencies, some of those are 100 hertz measurements, but they are like bursts. So you might measure 5 minutes at 100 hertz, and you might do that when the wind is high. And so some of these are triggered measurements. But it comes down to that balance. There's not a lot of value in measuring faster if you're not going to use the data for anything. And that's especially true in utilities. R&D sites may be a little bit different. You might want to measure faster because you don't quite know how your analysis might go down the road, and having those more frequent measurements could be useful, but the majority of the industry, no.
Thank you. I have a question for you. A moment time ago, you mentioned measure the current down to the microampere or milliampere. The current.
The V10 measurement?
Yeah.
Yeah. 10 milliamps.
10 million. Okay.
So it requires sourcing 10 milliamps and then measuring the voltage.
Yeah, you cannot go down to the nanoampere.
Well, you can for sure. Let me go back to that slide.
Oh yeah, that.
Okay, so here.
Yeah.
So when we look at these, here we see the largest
variation, right, between the two conditions. If you go down into nanoamps or microamps, you don't see a lot of change. And so, yes, you could put a much lower current, but the ability to discern the damage that was introduced is lower. So 10 milliamps seem to be about the right distance. So that's kind of here. And so here is the delta between the worst case condition and the original. So you can kind of see how much voltage you're working with.
Oh, okay. Thank you. Thank you. I see. So it means you sell the design the measurement device, and meantime you do the testing as well. Your company.
So this one is conception of the measurement. Right now, my company has not built any hardware for this yet. Most of this work is being done at UCF in their laboratory under Dr. Colvin. But the vibration study, we're building the hardware for that. Nobody had that equipment, and so for us to conduct that study, we needed to come up with it. And I think that's one of the great things about being in a measurement field, is that you can talk to other scientists or other people doing data analysis and understand what the need is and where there's a gap, and then try to build that hardware to fill in that gap and really improve our understanding of the technology. And so, that's what I find most interesting in all of this is having a conversation over coffee with someone and they'd be like, I'd really like to measure this thing. And you go, I know how to do that for you, or I can build that. And that's a really entertaining part, for myself.
Thank you. Any more questions? No more questions? Yeah.
How long does it take y'all to develop a new standard of measurement?
Standardization is the big time frame. So you can develop a measurement technique in a day if you want, right? If you have a really clear vision for what you want to do. But then it's the proving it and getting standardization, which takes a lot of time. We're now coming up on probably a year of measurements for this V10 technique, a couple papers, a couple presentations, right, where we're getting some feedback from industry and plant owners about it. And the vibration work, we've gotten, I think, about a year's worth of data, but are just now starting the analysis. And so, that can take a while. And so some of these techniques can be a PhD thesis in itself. So, it really depends on the group that you're working with, how motivated they are, how much interest there is in the industry. And if all those things are good for you, then stuff can go quickly. But a comment on standardization, there is a kind of an international group, IEC, the International Electrotechnical Commission, which really covers the standards for PV industry at all. And then often those standards are adopted by UL or others for testing. And IEC standards can take years to develop. And it's really because you've got this global group of people trying to come together on a standard and what the language is and what the technique is and all of that. And it can be a very onerous process. Not really my favorite thing to do. I prefer the development side, and I'll let other people work on the standardization, but that's my preference.
Thank you. Any more questions? Oh, thank you so much. Thank you, ma'am. Another round of applause.
Thank you for having me.
Thank you.
I appreciate it.
Looking forward to working with you on more proposals. Yes. So the Dr. Senior,
Yeah.
you fall asleep. So your turn.
No, correct.
Your turn to introduce our summer program. Thank you so much, Ryan. Thank you very much.
Yeah, thank you.
Very great talk. We learned a lot.
I'm glad. Do you want me to go? Or
No, you can stay.
Oh,
You
okay.
can stay with us.
So yeah, thank you, Ryan. Great talk. This is just for the students. We just wanted to let them know of a couple of opportunities that they could apply for. We have coming up this summer. There is basically a couple of training opportunities that are going to take place both under this specific program here on solar energy. There's going to be a week of training from May 12th to May 16th at Albany State University. And then it's going to be followed up by another week at the University of Central Florida. So if students are interested in those opportunities, they can apply here. And I believe Dr. Liddy has links that she can also share. Maybe she has shared those with you already. And in addition to that, there is kind of the sister program, but this is happening May 6th to May 17th, or maybe I think it's longer than this, right? 6 weeks, is that correct?
Yes. Georgia Tech is 6 weeks. Yes.
Yeah, it's a 6-week program. So that may be actually, I think that should have been June 17th. But this is the sister program in Georgia Tech, and this is not solar energy, but it's more, I believe, on I'm losing my train of thought here. Dr. Liddy, which I think it's basically they're working on.
looks like storage.
Yeah, batteries. Dr. Liddy, do you know exactly what the program is in Georgia Tech?
Georgia Tech, Dr. Su said start the May 23rd and last 6 weeks.
Right.
Yeah.
So this is another opportunity, and there are also longer term internships. So this is the website if you guys wanted to learn a little bit more about this program that Dr. Liddy and myself are running. You can just go to this website and it tells you a little bit more. But you can also find additional internship opportunities here. Some on data analysis and machine learning coming up this summer as well. This is longer. I think it's a 10-week opportunity, 10 weeks opportunity. So, and it comes with all of them comes paid with a stipend. So anyway, it's exciting. If you want to be part of something exciting and learn some new skills, feel free to apply.
Okay, thank you. That's it.
Thank you, everyone.
Thank you.